Hey y'all, today we're going to take a look at formal charge. Now, formal charge is used when drawing Lewis structures and when trying to determine the best possible Lewis structures if you have a couple of options. So let's take a look at, number one, how we calculate formal charge, but number two, how we would then utilize it when comparing different possible structures. Now, carbon on the periodic table has 4 valence electrons. In carbon here, it has 0 electrons in lone pairs, and it has 8 electrons total in bonds, right? And remember, each covalent bond represents 2 electrons. In formal charge, we're considering one to be owned by the carbon and one to be owned by each of the hydrogens, which means that carbon owns 1/2 of 8 valence electrons, which would be 4. This means that carbon's formal charge in methane is 0. Hydrogen. Now, hydrogen on the periodic table has 1 valence electron. It has 0 electrons in lone pairs, and this goes for all 4 hydrogens. Each hydrogen you'd theoretically be accounting for separately, but in this case, they're all identical based on how they're bound, which means we can just do one calculation for each of the hydrogens. So hydrogen, in this case, has 0 valence electrons in lone pairs. And each hydrogen owns 1/2 of the electrons in each bond that it has, which in this case only is 1. Each hydrogen only has the 1 covalent bond, so that's 1/2 of 2 electrons. This means that each hydrogen has a formal charge also of 0. So in methane, the formal charge of the carbon is 0, and the formal charge of the hydrogens are all 0. In terms of formal charge, a formal charge of 0 is very stable. In fact, when comparing formal charges, and we're going to talk about this again in a moment, what we're looking for is a situation where the formal charges of a compound all add up to the total charge of the compound. In this case, methane has a total charge of 0, and the formal charges of carbon and hydrogen add up to 0. So that's good. But also we're looking for the formal charges to be as close to 0 as possible. That's a more stable situation. So the more stable compounds are the ones with the formal charges which are all closer to 0. If there is going to be a formal charge, a negative formal charge will be most likely on the most negative or electronegative atoms, and the most positive formal charges are going to be on the most or the least electronegative atoms. So if you're going to have a negative formal charge anywhere, you want to find the most electronegative atom for it. And if you're going to have a positive formal charge anywhere, you want it to be on the least electronegative atom. Now let's look at the next molecule, which we Lewis diagrammed in the last video. We're going to look at ammonia, NH3. So remembering ammonia here, it's made of nitrogen and hydrogen, and the nitrogen has 3 covalent bonds and a lone pair. So let's take a look at how we would do the lone pair here. So I'm going to look at the formal charge of each atom in this compound. Now, nitrogen on the periodic table has 5 valence electrons. In this case, the nitrogen has 2 valence electrons found in lone pairs. It only has 1 lone pair, which has 2 valence electrons, which means I'm going to subtract 2, because each electron in a lone pair counts by itself as an owned electron. And then the nitrogen has 3 bonds, 3 covalent bonds, single covalent bonds. In this case, each covalent bond, again, has 2 valence electrons accounting for it, which means that you're going to have 6 valence electrons found in lone or in the bonds. 5 minus 2, and then 1/2 of 6. All right, so 5 minus 2 minus 3, that gives a formal charge for the nitrogen of 0. Now, for the hydrogens, it's the same as it was in the last structure. Where each hydrogen has a formal charge of 0 as well. The total formal charges of this compound, 0 for nitrogen, 0 for each hydrogen, they add up to 0. Therefore, this is going to be a stable or a very functional Lewis structure. Now let's look at carbon dioxide. And I want to look at carbon dioxide for a couple of reasons. The first reason is because it involves not single bonds, it involves double bonds, but also because I want to show you a couple of other options. So carbon dioxide, if you remember, looks like this. And in this case, the formal charge of the carbon is going to be 0. And it's going to be 0 because of the fact that it has 0 lone pairs around it and 8 total electrons, valence electrons, found within the 2 double bonds. Remember, double bonds count for double bonds count for 4 electrons total. In this case, it has 2 double bonds, therefore 8 electrons. The formal charge, therefore, for carbon here is 0. Each oxygen on the periodic table has 6 valence electrons. Each oxygen has 2 lone pairs. That's a total of 4 valence electrons. And each oxygen has 1 double bond, which is going to be 4 total electrons, oxygen owning half of those. Therefore, each oxygen has a formal charge in this structure, also of 0. So in carbon dioxide, you can see the formal charges are 0, but that's where it's properly drawn. What if it wasn't? Let's take a look at another option to see if maybe there was a different way we could draw carbon dioxide. So let's take a look at this structure for carbon dioxide. Now, if we look at this structure for carbon dioxide, you'll see that the carbon in this case, again, should have 4, but it has 4 electrons in valence shells, or I mean not in valence shells, but in lone pairs, sorry, and it has 2 bonds. So if we look at this carbon atom, its formal charge is not going to be 0. The formal charge of this carbon atom is in fact going to be -2. And if we look at the oxygens, again, should have 6. Each one has 4 valence electrons in lone pairs. And each one only has 1 owned electron within each chemical bond, or each single bond. In this case, that's just 1. So in this case, each oxygen has a formal charge of +1. So why is this not the correct structure? Well, first of all, in the top structure, carbon dioxide has minimized formal charges to as close to 0 as possible. In this case, they are 0. Secondly, the reason that the second structure would not work is because even if all of the formal charges add up to 0, which they do, 1 carbon of -2 and 2 oxygens of +1 have a formal charge total of 0, that's good. But this is not the most stable structure because those formal charges, first of all, aren't 0, And second of all, the positive charge is on the most electronegative atom, and that shouldn't happen either. So if we're going to have an isomer type situation, we're going to apply it similarly. You're going to be given different options for compounds, and you'll have to make a decision based on formal charges, which one is the best. And again, it's based off of which one has the smallest formal charge and where the formal charges all add up to the same as the charge of the compound. Okay, let's look at an example now where I'm giving you 3 different structures, and your job is to figure out which is the best one. And when I say the best, what I really mean is the most stable structure. Most stable because its formal charges are minimized as close to 0 as possible, and where all of the negative formal charges are as best as possible on the most electronegative atom, and the positive formal charges are on the least electronegative atom. So let's look at these 3. First thing we want to do is calculate the formal charges for each atom in each structure. We need to show our work for this. It's actually a really big deal. I'm going to do it in a different color. So for nitrogen, in the first structure, again, it should have 5 based on the periodic table. It has 4 in lone pairs, and it has a total of 4 in the double bond, of which it owns 2 of them. Therefore, if we do this math, 5 minus 4 minus 1/2 of 4, we get a formal charge on the nitrogen of -1. The carbon in this case has a formal charge of 0, 0 electrons in lone pairs, 8 total electrons in the bonds, the 2 double bonds. Therefore, its formal charge is 0. The sulfur in this case also has a formal charge of 0. It has 6 valence electrons on the periodic table. It has 4 in lone pairs. It has 2 that it owns within the 2 bonds, the double bond. So its formal charge is 0. So these are the formal charges for the first compound. Let's do the same thing for the next 2 compounds. You do it for each of the next 2 compounds. Pause the video, find the formal charges for each, and then when we come back, we'll go through. All right, so formal charge for carbon is going to be 4 minus 4 minus 1/2 of 4. So formal charge for carbon in this compound is going to be -2. The nitrogen in this case is going to be +1. And the sulfur is going to be 0. In the final isomer here, let's take a look at it. Okay, so the last structure here, carbons is going to be -2, sulfurs is going to be +2, and nitrogens is going to be -1. So if you had a pick of these, which is the most stable, again, you're looking for the one where you've minimized the formal charges as close to 0 as possible, and where the negative charge is on the most electronegative atom. Well, at least as best as possible. In this case, the first isomer in the top left there is the best structure. We would pick that one because it minimizes the formal charges of each element. So it's all of them add up to -1 in all three compounds and all three isomers. But in the first one, the formal charges of the carbon and sulfur are 0, while nitrogen's is -1. That's the best case scenario here. Also, nitrogen is the most electronegative atom in this compound, and it having the formal charge of -1 is also the best option. So therefore, we would be able to pick that structure as the most likely. And if you were to draw that structure from scratch, you'd be expected to be able to use formal charge to decide how to create bonds, double bonds, and lone pairs around different atoms. We're going to keep using formal charge as we go through, because in the next video, we're going to look at more complicated structures, and formal charge is going to come into play big time. I hope you enjoyed this video, and I will see you in the next one.